All right. Hello, I'm David. It's semester 1, 2019. Right. And this is a revision seminar for Engineering Maths IIA. Welcome to all of you who are in person and to everyone listening online. I had a most interesting experience the other day when one of the current students told me about me talking to myself in the future in one of the past revision seminars, and it was very useful, actually. So it'll happen again, I'm sure. So, people have put some things on the board. I put some things that people asked me on email, and you guys have put some things on the board. And together it seems to cover most of the course, so I'm not going to be able to cover all of it. So, the first thing I thought I would talk about, because I already thought about it last night when someone asked me, was the combination of, well, basically picking particular values. Not particular values, particular solutions when you have a homogeneous, non-homogeneous differential equation. So I'm going to do that first. I should tell you that the first revision seminar on the webpage has a little summary of all the different kinds of methods you have of solving differential equations, a little chart of which one of when you use them and what they're for. That might be useful for you if you want to go look that up. Okay, so all right, homogeneous and particular solutions to DEs. Well, I'm also very excited. It's not very important, but we've got new Maths Learning Centre pencils. The old ones were crap, and these are nice. And have recycled newspaper as the barrel. They're lovely. We have our names on the pencils because people take them, so we might as well have Maths Learning Centre written on them. So it's advertising. We need to put it on the spoons. Oh man, I'm not doing well today. Right, homogeneous and particular solutions to DEs. So the idea is that there are differential equations where you have, in fact, has someone got their lecture notes or slides or something? Or am I going to have to look it up in the great big book of everything? Oh, that's better. The slightly smaller book of everything. Okay. I'm just having a quick look through to see if I'm making sure that I'm all right. All right, cool. Whoa. Oh, look, that's my handwriting. Constant coefficients, method of undetermined coefficients, thingies, variation of parameters. Oh, okay. Okay. Right, now I know where I am. So, the beginning of the second order differential equations bit of this course was, so there's the first bit. So second order and above. And we have two situations. We have ones where we have sort of like a function. No, the P doesn't normally go there. Sorry. I've lost my eraser. We have a function y, and we don't know what it is, but we do know a formula involving its derivative. Like that. And it's traditionally written like this. And these P and Q and R are functions of x. And we have three different words that we could say about this. We can decide whether these are constants, And if this is 0, it's called homogeneous. And if it's not 0, then it's non-homogeneous. And all of them tend to run by solving the homogeneous one first. So we're always going to do this first. So we're going to solve that one first. And this is called a homogeneous equation. And then we're going to think of, in some way, we're going to have to think of a solution to the original one. And so that's going to give us a solution which your lecturer normally calls YH, I think. Is that right? And the point of this is that a very important point to remember is that this Y is not the same as that Y. So the Y in here, when I run it through this formula, produces Rx. But this Y, when I run it through this formula, produces 0. And that's important to remember. This is not a solution to that. It's a solution to a whole different equation. But the reason why we want it is that if you have something that is a solution to this plus this one, then when you run the solution to this through here, you get Rx. And when you run this through here, you get 0. And so when you add them together, you're going to get Rx anyway. And so you'll be able to create new solutions from the one solution you already have. Okay, so you're going to get homogeneous solution, the solution to the homogeneous equation. And then 2, we have to think of one particular solution to the original equation. You know, the one that was equal to Rx. And that's called YP. And then you go, all solutions to the original are YH plus YP, or YP plus YH, it doesn't really matter. So the idea is that you run this addition thing together through this formula, and the part that's YH will go to 0, and the part that's YP will go to Rx. And so it'll come out to Rx after all, and therefore be another solution. So it's a lot of the rest of the course is about the difficulties in dealing with this and dealing with this. This bit's we're fine, we can just add them together. And so you first started out by dealing with this when these are constants. So we're going to do that first. So with the constant coefficients, when you do that first step, it's just the letter P. It's more like that, and they're just letters as opposed to functions, and these are constants. And it doesn't really matter whether there's a coefficient at the front or not in this particular story. And so you're going to first turn it into the homogeneous one. I really wanted the one to be down here, sorry. This is your start. So first you solve this one. That's your homogeneous equation. And the way that you go about solving that is you imagine what would happen if y was e to the power of something x. And the reason you do that is that e to the power of, say, lambda x, for want of a better letter, will tend to be almost the same when you differentiate it. So if you differentiate it, it'll just get times by the lambda, so it's roughly the same as it was before, and that will mean that we'll be able to, if we focus on the functions that don't change very much, when we run them through this process, it'll be easier to find them. That's the idea. And from a linear algebra point of view, they tend to be eigen things. Eigenvectors don't change very much when you multiply them by matrices. Eigenfunctions don't change very much when you run them through differential equations. So that's why we're using this, this lambda, because that's what we used when we did it in eigenvalues. So what we're going to do is we're going to write a characteristic equation, and it's going to replace all of the y's with lambdas and all of the and all of the derivatives with powers. So the 0th derivative will be lambda to the power of 0, and the first derivative will be lambda to the power of 1, and the second derivative will be lambda squared. And you don't technically need to rearrange it to be equal to 0 to do this. You can just do that however it's arranged at any point, and it will work out fine. And then you solve this and you get two solutions, and you'll get, lambda equals something and something. And you'll get these two solutions, and depending on what kinds of solutions you have, will dictate how, because of the wisdom of those who have trod this path before us, that will dictate what the solutions are going to be. So if lambda is two real numbers, like a and b, both real but different, you'll get y equals like e to the ax and y equals e to the bx as two possible solutions. And if lambda is a and a again, where they're both real, then you'll get y equals e to the ax and y equals x e to the ax. You can't just use e to the ax twice because we're going to need two. The reason we're going to need two is because it's a second order differential equation. If it was a third order differential equation, we'd need three solutions. I haven't even created all the solutions yet. I just want two solutions at the moment. So once I've got two solutions, I should be able to combine them together to get all the solutions. And if you get in non-real like that, not real, then you do e to the alpha x cos beta x and e to the alpha x sine beta x. So you get all these different possibilities for the two solutions you can get. But as long as you have two, and as long as they're not multiples of each other, then you should be able to create all the rest of the solutions from them. And then you say, so YH is going to be something times whatever the first solution is plus something times whatever the second solution is. And whichever two solutions you pick, they end up here. So it could be a e to the ax, b e to the bx, or it could be a e to the ax, b e to the bx e to the ax, or it could be a e to the alpha x cos beta x and b e to the alpha x sine beta x. Doesn't really matter. But you combine them together and you get that thing. This is a general picture of what you do. And then the hard bit happens usually next. Okay, so that's my homogeneous. So that's all the solutions to the homogeneous equation. And then the second step, we have to find any one particular solution. To the original. So we need something that when we run it through here, it produces Rx instead of producing 0. And the main way of doing that is using the method of undetermined coefficients. But there is another way of doing that as well, and I'm going to talk about both of them. So, undetermined coefficients. Or variation of parameters. And these are two methods for producing a single particular solution to the original equation. We just need one. I mean, there's a sort of a method 0, which is you happen to think of one and it works. Or they give you one. All right, so method 0 is you happen to have one already and someone already did it for you. It's always so important to watch out for that in an exam when they've done part of the work for you. Or you just know. You look at it and go, oh, it's obviously e to the 3x. Most people don't know that anything is obviously e to the 3x, but you might one day. Okay, so any one particular solution to the original will be fine, and these are two ways of doing it. And these two ways are designed, they're very similar. No, they're very different. But there is one thing that they have in common, which is you are going to have some unknowns, and you're going to figure out what the unknowns have to be in order to work. Both of them have that feature. Okay, so let's actually do it. And I'm not going to write the entirety of coefficients because I can't be bothered. So undetermined coefficients works best if I do an example, the idea is that you look at the Rx, you think of something that could possibly produce that when you differentiate it a couple of times, and then you figure out what constants it has to be. So look at Rx. Imagine a sort of a shape for Y. To get Rx, when you do Y double dashed and Y dashed, and find the unknown coefficients. That's the philosophy, and that's why it's called undetermined coefficients, because we have some coefficients that we don't determine at the beginning. They're not determined at the beginning, and we determine them at the end. And so the idea is that because of the wisdom of the people who have trod this path before us, which is basically how the whole of this differential equations bit works, because of the people who have trod this path before us, they have figured out what, if you see a particular shape for Rx, what the shape for the Y should be to make it work. So it goes something like this. If Rx is like e to the something x, then the Yp should be some multiple of that. We don't know which multiple, and that sort of makes sense. If you differentiate e to the mx any number of times, you'll just get an e to the mx, and so it should be possible to figure out exactly which multiple, when you times it by the p and the q, will come out to the answer that you're thinking of. And it doesn't even matter whether it's just straight e to the mx, it'll be any multiple of this will be fine, you just choose a different multiple. Okay? So if you get cos of some multiple of x or sine of some multiple of x, then you'll try both. And magically it works. The reason you try both is that if you differentiate cos twice along the way, you're going to get a sine, and so the answer at the end is going to possibly produce a sine, and you might need a sine to cancel out that sine so that you end up with a cos at the end. So, there you go. Any of the derivatives and integrals of your function should sort of, any of the integrals of your function should sort of be in the answer, basically. And if you have something that's a polynomial, then the y should be a polynomial of the same degree. So as an example, if the Rx was like x cubed plus x, then I would choose the Yp to be something plus something x squared plus something x cubed. I would have something that is also a cubic polynomial, but using all the possible coefficients it could possibly have. All right, and the only other rule that I know of, if I'm doing this right, is that you have to try, if you have anything that's a product of these two, then you do a product on the other side as well. So if you have Rx is like two things multiplied, then the Yp should also be two things multiplied. So if you have an e to the mx cos mx, then you'll put an a e to the mx times cos mx a plus sine mx. Okay, something like that. You just need enough coefficients so that each of the separate bits have things. So just as an example, if Rx was e to the x sine x, then my Yp I would go e to the x sine x and e to the x cos x, both of them, like that. And the only other rule is if you've already covered the solution that the format that you're thinking of when you did the homogeneous solution, it's not going to work. Like if my homogeneous solution already had e to the x sine x, then when I ran e to the x sine x through the formula, it would come out as 0 and it won't come out as Rx. And so I can't use it if it's already been used in the homogeneous solution. And the normal way of dealing with that is to multiply by x. So, if it's already covered by the homogeneous solution, multiply by x until it's different. So if you've already covered x and if you already covered e to the x and x e to the x and you need an e to the x, you're going to have to go x squared e to the x. You need to get until the power of x is bigger than the one you've already used. And the reason is because you can't use anything in the homogeneous because it's a solution to something different. And you need something to be a solution for this one. Now, you haven't been given any other formats. So if you see something that is not one of these, you could try, you really could, like if you saw something like e to the x over 1 plus x, you could try something of a similar shape, but it really most of the time won't work. If there were ones that worked, your lecturer probably would have told you. So there are situations when just making a guess of something that's a similar shape to what you've got just isn't going to happen. And it usually causes problems when there's things on the denominator. They always cause problems. And so what we're going to have to do in that situation is do variation of parameters. Do you want to see an actual example of me doing this? Okay. If I don't do that, if I don't ask you if you want an example and you want one, ask. Okay? I'm all good with you interrupting me if you need to. There's a limit to how many interruptions I can cope with, but you know, maybe wait till I finished a sentence. I'm happy for you to interrupt and say, hey, before you move on, could you do this, if you're thinking of it. Okay, so let's do a proper example. Okay, so I'm going to, do you want me to include the whole bit where I do the lambdas as well? Or am I okay for me to skip that bit? No, just saying yes when I've asked an either or doesn't help. Okay. Okay, give me a second. I'm going to put numbers in here in a second. I just need to... Do you want me to do one that's really complicated? Yeah. Okay. So in what situations would the thing just here cause you the most pain? Polynomial and cos? Right! We're on. I need more space then. Okay. How's that? Sweet. This is going to be fun. Okay. So, I'm just going to put some numbers here now. Give me a moment. Yep, let's do that. Okay. Oh, no, let's not do that. Just a second. Sorry. I'm just going to need another bit of paper to figure out what I want to do. Oh. No. Give me a sec. Crap. Oh, for the sake of frill. I'm just going to start again. Okay. Okay, that's the one I'm going to do. Nope. Okay. You can see how hard it is for people to write your exam. I'd love to see them do that on the spot like I did. Okay, so this is our differential equation. We don't have any initial conditions that tell me what y is at certain spots, so the only thing I can do is figure out a general solution. If I did have initial conditions, I wouldn't deal with them until I had the general solution anyway. Ignore them completely until the very end. So here we are, and the first step is to deal with the homogeneous equation first. So we have y double dashed plus 64y is 0. That's our homogeneous equation, and it has a characteristic equation, which is lambda squared plus 64 equals 0. So if this had a lambda in it as well, I'd probably have to do some wicked factorising or the quadratic formula or something, but because it doesn't, I can just do this. So when I square root the minus 1, it becomes a plus or minus I, and when I square root the 64, it becomes an 8. Okay, so just so that I've being absolutely clear, the real part is 0. And so that means that my solutions are going to be e to the 0x, or t or whatever it was an x, okay. E to the 0x cos of 8x and e to the 0x sine of 8x. So the real part ends up in the power of e, and the imaginary part ends up in the multiple inside the sine and the cos. Okay, and so now what do I have to do now? Now I need to do this. And we technically don't need the e to the 0x's because the e to the 0 is 1. Cool. That's our homogeneous solution. Anything of that format, if I run it through this, this formula here, the y double dash plus 64y, will produce 0. Which sort of makes sense. If you differentiate something twice when it's sine or cos, you end up with minus what you started with, except with this multiple out the front. Okay. So the next step is to find our particular solution. So what we need to do is we need to look at this bit and try something that's similar. So first we're going to try this. So it'll be something plus something x times cos of 8x. Plus, we'll also have a sine of 8x as well, I guess. So if it had just been cos of 8x, I would have had just something cos x plus something sine x. If it had been just half of x plus 3, I would have done a plus bx. But because it's both, I need to do both. That's what I would do. So you could have done a plus bx times c cos x plus d sine x. That would have worked fine as well, I think. I just feel better about this one. It's going to be easier for me to differentiate. I do have a problem though. We already have an a cos x, 8x, and we already have a c sine dx here. They're already part of our homogeneous solution. So I can't use them. All right, but a cos bx and c sine 8x are part of YH. So I can't use them. So if you were doing it in your exam, you probably even wouldn't write this bit down. You wouldn't write it down at this point. But I just need to put it here in the notes so that someone reading it in the future knows what's going on. So I'm going to have to bump everything up a power. So if this a has to become an ax, but then I'm going to have to bump this up to an x squared because I already used the ax. I think this is how it works. We'll see what happens, eh? All right. Sweet. So it should be possible to find out the correct values of a, b, c and d so that when I do run this through my differential equation it comes out to exactly half of x plus 3 cos 8x. Okay. So let me just have a look. I'm going to need y double dashed, so I'll need y dashed along the way. If I was extremely clever, I could probably write down double dashed on the, without doing the bit in between, but I would almost be guaranteed to get something wrong, so I'm going to do them properly. So, product rule. Sweet. So I differentiate that and keep the cos 8x, but then I'll have to keep this and differentiate the cos 8x, which would turn it into a, do you know what, I'm going to just put brackets, minus sine 8x, and because of the train rule I'll have to multiply by the 8. Okay, and then I'll do the same thing for this. And then I'll keep this, and then that will become cos of... Beautiful. I feel it will probably be productive to collect some like terms. So I've got a cos 8x here and here, so I'm going to have a plus 2bx plus 8cx plus dx squared times cos 8x. And I'm going to have c plus 2dx plus 8. Oh, no, 8 lots of this. There'd be an 8 here too, wouldn't there? Beautiful. C plus 2 dx minus 8ax minus 8bx squared sine 8x. I have a feeling this would be too long for an exam, but at least we know what's actually going on. So now my y p double dashed is going to be 2b plus 8c plus 16 dx cos 8x plus a plus 2bx plus 8cx plus 8dx squared times minus 8 sine 8x, and then we're going to get the derivative of this keep the sine plus keep the original and differentiate that. Okay. And yp double dash plus 64 times the original y is supposed to come out to this. All right. So let's see if I can do this all at once. I'll deal with the causes first. This has got a cos 8x, this has got a cos 8x, and this has a cos 8x. And so I'm going to get 64 of this one. And then the yp double dashed, which is this one. Times cos x, cos 8x, plus, oh crap, I did all that off screen, sorry. Plus, so I took this bit here, times 64, which is that bit there. No, not that bit, this bit, times 64. And then I took this bit, and this bit times 8, and that gave me this. And then there'll be something times sine of 8x. Yeah. Brilliant! So now I would generally equate coefficients. Like this is supposed to come out. I'm sorry, I'm just going to skip that bit. I've given up. I don't care anymore. Okay. So all of these coefficients that go with the sine 8x, they're all going to have to be 0 because I don't have any sine 8x's here. And the coefficient, the constant coefficient that goes with the 3 cos 8x is going to have to be 2b plus 8c plus another 8c. That has to come out to 3. And so I'm going to equate coefficients now. And then the x squared term has to be 0. So we're going to get so if I just, there's going to be more of them, but so far I've got the constant term, constant times cos 8x, and so I can get a 2b plus 8c plus another 8c. They're all the constants, and that comes out to 3. And then I have x times cos 8x, and I get 64a plus 16d plus another 16d minus 64a is a half, because that's the coefficient of x cos 8x, x squared. Yep, I'm x squared cos 8x. Crap, 64b of them, and minus 64b. Oh, that's 0. Interesting. It won't tell us what that is at all. Maybe I didn't need that. Okay. And that's supposed to be 0 because there are no x squared terms, x squared cos x terms. And then there's going to be the constant times sine 8x, which will be something equals 0, and then the x times sine 8x, which will be something equals 0, and then the x squared times sine 8x, which will be something equals 0. And that'll be enough equations to figure out what all of the letters have to be. And in fact, my instinct tells me that I had 4 unknowns to begin with, in which case I only need 4 equations. So I reckoned that I probably didn't need the x squareds at all. So the fact that I reckon along here I might end up finding out that it doesn't make any difference what b is. I won't be able to find out what b is, in which case I just choose b to be 0. I'm really going to have to do it, aren't I? No? Okay. So at this one we've already figured out from this one that the d has to, we can figure out what d is from that one. So from, give them numbers, 1, 2, 3, 4, 5, 6. So equation 2 is that 32d is a half, so the d is actually 1 over 64. So I know what d is, and hopefully there's other equations down here that have d in them, and then I can use that to figure out what something else is. And once I've figured out what some of them are, I can figure out what the other ones are, and then I'll know what everything is, and I'll have an answer. Right. But it can be this long. You are allowed to equate coefficients of functions. Just keep track of all of the different functions you've got involved. That's the bit I wanted to make sure that you saw when I chose this example. Yeah, and I'm just going to put a note here for this one. It might mean we can't find B, in which case we can just choose it to be whatever we want. But you have to combine it with the other equations just to be sure. But it might also mean that you get a contradiction. If you get a contradiction, you end up with like 0 equals 1, then that meant that your original choice was wrong. And you probably should have times it by x. Yeah. Okay. Well, that was fun. So the big question is, if it's not in one of those formats and you can't do this thing, then how do you figure out what the yp is? And that's what the variation of parameters is for. So if we had a big what if, what if it's not the right format? Well, in that case, you have to do variation of parameters. And this semester there was an assignment question that looked like it was one of these, and we all tried very hard to find the correct undetermined coefficient format, and none of them worked. And then it turned out that actually variation of parameters was the go. But it wasn't until like the second day of helping students in the Maths Learning Centre that we figured that out, which is why I sent people an email about it. So, okay. So variation of parameters has one thing about it that's similar, which is that we're still going to create something that has some known bits, but then some unknown bits, and we're going to figure out what the unknown part is. So variation of parameters goes like this. So let's see if I can find it. So it's designed to find, so basically I find yp using yh. So here's the, it's kind of interesting. Even in this format here, this one that I just did, even in this one I just did, the format that I'm using has the homogeneous solution as part of it. It has the cos 8x that was up in the homogeneous and the sin 8x that was in the homogeneous. And what I need to find out is the correct function to multiply them by to produce the yp. Now I know that it's got to be something like it's linear or quadratic, and so it probably can be quicker to figure out what goes in those positions by just putting unknown coefficients and seeing what happens. But the variation of parameters directly finds what functions go in those positions instead of using unknown coefficients. And so even if the thing that you're looking for isn't related, even if this had been a cos 7x in the R, I could still technically have been able to do it because you can. It would have been really hard probably. So I'm going to do this one, redo this one, doing the variation of parameters. It's going to be easier to see in an example. Okay. So we already have the YH. Thank you. That would be a different thing entirely. And that was A cos. So this is going to make it a particularly good candidate for variation of parameters because part of my homogeneous solution is already in the Rx. So I reckon it's going to work well. It might turn to a pile of dren, but you know, you just figure it out when you get there. You should all watch the TV show Farscape to find out what dren means. It's probably pretty obvious from where it was in the sentence. We already have that, and so what we're going to do is we're going to hope that that my YP is, and I just want to use the same notations for this, is U is this. So I'm going to hope that it is some combination of the homogeneous one. So I'm going to take the two bits that I use to create it. I don't need the A and the B. Technically, I sort of use, you know how I wrote them down separately before I put the A and the B in? Those are the bits I use. So these end up here. And then I'm going to make some fairly, I don't know where they came from, some fairly stupid assumptions that make this work. And I'm going to trust the people who have come before me who will tell me some useful things. So, the way this is going to work is I'm going to technically do what I would normally do when I did constant, undetermined coefficients, and I differentiate this and run it through the equation to see if it comes out to Rx. And I'm going to try and choose the correct functions that make it come out to Rx. But I'm going to have to make an assumption along the way. But I'm not actually going to do any of that because I know, well, at least if your lecturer is similar to past lecturers of this course, they don't really want you to prove that this works. They want you to be able to use the actual outcome. So I'm just going to put in brackets here. You know, what we're imagining here is we're going yp dashed equals whatever, y double dash p, yp double dashed is whatever, and we sub it in to the original. And then we make an assumption along the way. You know, assume that u dashed of cos 8x plus v dashed of sine 8x is 0 because we can. It's just an assumption that we make so that it works. And do some things, and we'll get a couple of, we'll use this equation and the equation we get from subbing it in. We'll take those two, and that will allow us to find out that u dashed equals thing and v dashed equals thing. That's what's going on in the background. But the things that it works out to will always be the same. And so we're going to do it. We're just going to do this. The u dashed will be equal to minus the other solution times the r. Can I call this y1 and y2 so that we can do this properly? And let's call this r. Okay, so I'm just going to give them names so it's easier to talk about, and then I'll sub it in a minute. Okay, so what I'm going to do is I'm going to write down the formula. So we're going to go, it's minus y2 times r over w, and the v dashed is y1 times r over w, where w is the determinant of this. Yeah. That's the formula for variation of parameters. And I'm pretty sure that this will be on your formula sheet in the exam. Yep. Pretty sure. They have in all past exams, so... But just so that you can recognise it when you see it, notice that originally the u went with y1, and at the end it uses the other one in its solution. It's very easy, even with the formula written down, to end up using u dashed with y2, with y1 here, but it actually goes with the opposite one. Of course, you could call this one u and this one v, and it would be fine, so it'll all work out. But it won't work if you don't put them with the correct ones at the end. So just keep track of the one that you use here is not the one that you join the u with at the end to find the actual answer. So we're going to do this. So our u dashed is minus sine 8x times half of x plus 3 cos 8x over... Oh, I really should figure out what w is, shouldn't I? Ignore that. We need to know what w is to be able to do this. W cos 8x sine 8x, and then we'll have the derivative of cos, which is minus 8 cos 8x, and the derivative of sine, which is 8. So it would be a sine by the time it would, wouldn't it? Too many sines and coses floating around. So that goes down there, right? They're the derivatives. Okay, good. Yay. And so when I do the determinant, I'll get this times that minus this times that oh, look at that. So I get 8 cos 8x squared plus 8 sine 8x squared, and cos squared plus sine squared is 1. Bang! Oh, that was convenient. Oh, lovely. Okay. Okay, so u dashed is now minus y2r on w, which is minus sine 8x times a half x plus 3 cos 8x over 8. Sure. So minus half of x plus 3 sine minus an eighth 8x cos 8x. Okay, and to figure out u, I'm going to have to integrate that. Fun. So we're going to have to do it by parts if we want to integrate that, aren't we? It's crap in both ways, this problem. Okay, but I can make it a little easier on myself. Sine 8x cos 8x appears when you do... sine times cos appears when you do sine of 2x. And so sine of 2 lots of 8x would be 2... So just a second, let me just do this. So I've just pulled an extra 2 here by dividing by 2 here as well. This is sine of 16x. That I can integrate. Well, I mean, I still have to do by parts, but you know. So u will be equal to the integral of this. And that'll be like FG, and I'm going to have to differentiate one of these and integrate one of them. So if I differentiate this, it'll become a constant. So that's what I want. I want it to be a derivative at the end. Okay, good, good, good. So my f is minus a 16th of half of x plus 3. And then I have to integrate the sign, which will become a minus cos. Ooh, over another 16. It's fun. And then I have to go minus, and the f dashed, minus 16 is still there. We'll have a half. And the integral was plus a 16th of... Right. And so I'm really hoping I did that right. I normally write down what the f and the g are separately on another piece of the paper so I don't get it wrong. So I've probably got one of my minuses wrong. I apologise. Bad exam practice to just hope it's going to be okay. Right. And so we're going to get, Beautiful. And we don't need the plus c, because we're going to multiply it by something anyway. That is, yep. We know what that is. Told you it would be a pile of dren. And so then my v dashed is y1r over w, which is cos 8x half of x plus 3 cos 8x over 8. And we'd have to integrate that to figure out what v was. Yeah. So v is going to have to be the integral of all of this stuff. Which will be whatever it is. And then I'm going to go, okay, so the yp is u times plus v times sine 8x. That's how we did it originally, wasn't it? Yep. And so we're going to get 1 on 16 squared half of x plus 3 cos of 16x minus 1 on 16 cubed times a half of sine 16x times cos 8x plus whatever v is times sine 8x. Yay! Really should have had one that wasn't quite so horrible, but maybe it makes you appreciate it when you get to your exam and it's easier than this. Right. So I think it would not be the worst plan if you couldn't finish it to do something like put a box there, but maybe say, you know, just call it like f of x or something, so that you could tell them what you were going to do if you couldn't finish it. Because there's probably a mark attached for putting it together correctly at the end. So even if you can't finish the middle, tell them what you would have done at the end. Every mark counts. Okay. Exams are not a natural state of being. You need to do everything you can to deal with that. Right. So let me just see if I can sum that up. The whole point of both of these things, this undetermined coefficients and the variation of parameters, is to find a particular solution. And technically at the very, very end, when you did this, there would be one more step, right? You would have to go, you know, therefore y is actually the a cos 8x plus b sine 8x plus all of this. Okay? Never forget that bit. The whole point of this is that in order to find the solution, all of the solutions to the original equation, I need to first have the solutions to the homogeneous equation and any one particular solution to the original. And the problem is that finding a particular solution to the original, well, that's the actual question you were trying to solve. You're just trying to shortcut it without trying to find all of them just to find one. And so there's two methods. One is to guess what it looks like, run it through the equation and figure out what the coefficients have to be to make that work by matching up coefficients. And the other one is to guess what it looks like as a function combination of the homogeneous solution, run it through the equation and magically produce this thing with the Wronxian in it. And that's how it works. The people who write your exams are likely to pick something that will have bits cancel out because they know you've only got 2 hours. Is it 2? Right. As much as a 3-hour exam is tiring, I wish they were still 3 hours because there's more time to deal with things and more questions about things that you might know when you didn't know this one. So anyway, that's my opinion about exams. Okay. Cool. That took a lot longer than I hoped, but at least we have an example of those two together. And just to let you know that the undetermined coefficients tends to only happen when these coefficients here are constants, but the variation of parameters can happen even when these are not. So there's a classic assignment question where they just give you 2 of the solutions to the homogeneous one. They just tell them to you. You don't have to find them yourself. And then you do the variation of parameters because they put functions in these positions instead of numbers. So that was what threw us off when we did the assignment. It was numbers here, and we thought, oh well, the number ones are where the undetermined coefficients go. But you can also use the variation of parameters when it's a number version as well. Okay. Cool. Right. Okay. I can hear some people saying stats. I think I need a change of scene for a few minutes, so maybe some stats for a while wouldn't be the worst thing. So someone has written there, how do I know what test to do? Who was that? Oh, right. What did you want to know about stats? What test to do? Okay, so that would require us to know what tests there are to choose from. So it would be cool if I had a copy of the thing that they are probably going to give you in the exam. Is this it? It's very fuzzy. Can I make that better? Marginally better. So this is apparently part of what you're going to be given in your exam in your formula sheet. Okay? That's why I'm just saying apparently and whatever. I really don't know. Lecturers don't talk to me. So I could ask them, but even then I probably wouldn't be allowed to tell you. I'd have to say, look in your own rules. So this is a list of various different well, it's not quite the whole test. It's different how to create the test statistic and the confidence interval from this information. Okay, so I'm just going to transcribe some of this. So I have okay, right, we can check them off as we go. I'm going to do them in a different order, and I'm going to give you something that is sort of idiosyncratic to me about how I think about statistics. So let me just step back a bit and tell you about some things. So the point of statistics is to deal with variation. So it's all well and good to have fabulous differential equations that allow you to exactly calculate an answer, a formula that will tell you what the temperature is at exactly any particular x and t. That's great. But the world just doesn't work that way. It's variable. Individual objects tend to be different from each other and different from themselves 10 seconds ago in random ways. And so the point of statistics is to deal with that and still be able to make predictions even though, and make decisions even though things are variable. That's the point. And so what the first thing that you did was to look at probability, and you have all these probability distributions that will describe, you never know what anything is going to be exactly, but you can know, well, it's more likely to be here than here. That's what probability is about. Okay? Good. And then the second part was about statistics, which is about decision making and predicting using variable data. Okay, so that's what it's for. And that means that it's useful to think about the ways that things can vary. And there are two, the information that you write down or record about objects will be different for different objects or different at different times. And so that's what we're interested in. When I'm working with the medical students, it's normally people, so I'm still going to draw that for you. But you can imagine this to be any object that you would like to measure. It could be people, it could be a robot arm, it could be a petri dish with stuff in it, it could be the chemical composition of something, it could be ice cream. It doesn't really matter. Okay? Depending on what sort of thing you're interested in. Statistics is often used in quality control situations, which engineers tend to end up doing in their jobs a lot more than they hoped. Yeah, that's what they end up with, and a lot of these were designed in that setting. But a lot of the statistical things that we know were designed for an agricultural setting as well, so it's about wheat yield and that sort of thing. So the thing is that anything that you write down about any object comes in two main flavours. There are things that are numbers, and there are things that are categories. I don't know if your lecturer talked about categorical versus quantitative variables in this course. Yes, no? Doesn't really matter. It's usually some place in year 9, 10, 11, 12 high school maths that they talk about this, and different disciplines call them by different names. Some people call them quantitative or scale variables or qualitative variables. Doesn't really matter, as long as you know which is which. Okay, so categories tend to be colours, the process by which you made them, or varieties of things, or days of the week. Put things in boxes, and then when I draw a picture of a category, it will be boxes. When I draw this symbol, it means I'm thinking about categories. And numbers, well, when I draw this symbol, it means a number. It's measured on some sort of scale. Okay, and they're the two main things about which objects can vary. So if you pick two objects, then if they are different, they might be, if you're thinking about categories, they'll either be the same category or they'll be different categories. That's the only way that categories can vary. They're either same or different. Whereas with numbers, if you pick two objects, you can go, oh, they are 6 apart, or 2.1 apart, or this one's twice as much as this one. Numbers, you can figure out how far apart things are. Categories, you can only decide whether they're different or the same. That's a question we might want to know. Are they the same? Okay. I wasn't expecting to talk about stats today, so I'm sort of, just give me a minute to deal with some of these. It may seem like I'm going on a tangent for a while. So the ultimate goal of most statistics is to figure out whether and how something affects something else. So most statistics questions are about this question. Does A explain changes in B? Okay, almost all statistical questions are about that. So you could have, does age explain, does the age of a person explain the chances of them having a heart attack? Probably. Does the variety of ice cream make a difference to the amount of fat that they contain? Well, could be, maybe, maybe not. Depends on whether you've been careful. And does does me changing this feature of the machine make a difference to the quality of the product that it produces? Okay, these are the sorts of things that we ask. And we want to know, can we use the changes in one thing to predict or explain the changes in the other? And so it's not just how it does, sometimes it's how does as well. It could be, there may or may not be a how. So ultimately they're trying to find formulas that take one thing and spit one thing out, but there's all going to be a bit of randomness. It's going to be, well, does A explain changes of B? Well, yes, it does up to a point, but then there's this bit of randomness and we don't really know what's going to happen to the B. Okay, cool. All statistical questions can be thought of in this way, and this is how I decide what statistics goes with what. But there is one last thing, and that is, how is your data arranged? Because you can ask this arrange your data to ask this question in multiple different ways. So if you thought that... give me a second. If you thought a particular treatment of your glass would affect its strength, then you could take the same piece of glass and do the treatment twice on it, once at the top and once at the bottom, and do the test on both parts. And really, okay, or you could take some bits of glass and do the one treatment on these ones and a different treatment on those ones, and that would be, the data would be arranged differently, and that would make a difference to what kind of statistics you can do. So data arrangement also makes a difference. So what's going to make a difference so far, just so we've got here, all questions are like this, and then what kind of variables are involved is going to make a difference to the kind of statistics you can do. And then the other thing is data arrangement. So data arrangement usually comes in two main flavours. One is you may have something where you're interested in how a category is related to a number. Okay, this is our question. I've just turned my thought bubbles into actual variables. It may be that every individual has this number measured twice. They're in both categories. Every individual has both a... My classic example I use with the health sciences students is that I take my friends and half of them, and I'm interested in whether chili makes a difference to their temperature. And so I give them a meal with chili, and then I also give them a meal without chili, and I measure their temperature twice. That's why I have no friends. It's all a pretend story. That's that story. Outcome measured twice, once in each category. Or you could have something where different individuals are in different, are in different categories. Outcome once and different individuals in different categories. Okay, these are the two main ways of arranging experiments to see how things affect things. The thing that you can do with this one is that for each individual you can subtract to figure out how much this changed by for each individual. Whereas this one you can't do that because everybody's only got one measurement. So, what kinds of variables are involved and how many categories are involved, and whether your data is arranged as repeated measurements on individuals or different individuals in different categories, that will tell you which statistics goes with what. Are you ready? Here we go. So this is going to be a completely different arrangement than what's in here. I will run down here. There is one other question you might ask, and you might not have anything affecting this outcome. And you might just want to know, well, it varies, but it varies around what? So that's your other question. You could just have B with nothing affecting it and want to know how does it vary. What should I expect, basically? That's the other kind of question you might have. Something where there's nothing affecting the outcome, it's just there. All right, so let me tell some stories. It would be really cool if I had some example questions that were engineering-y that I could talk through of making the decision. So when I do this with the med students, I give them like 40 examples and we work through all of them so that they can learn how to make the decision. So, but they're all medicine related. Okay, so this is the ones you've got and we're going to decide which of these go with it. So here's things. So when you say how do I decide, it's mainly deciding between a paired or a not paired t-test, right? That's the main problem. Yeah. That's this one. Okay. We do have t-tests, don't we? Oh, you guys don't have t's. Oh, you just... Yes, you do. Okay. Calm down, David. So, I'm just looking, just a second. Yep. Okay, so here's the thing. So I'm just going to go by question. What percentage of what percentage of packets of chips have holes in them? That would be a question that you might ask, right? And you'd be given various other bits of information, and you'd be saying, oh well, what we did is we took like 200 packets and 3. Let's just make it big. This is a very awful chip packet maker. My brother actually worked in a factory where they made chip packets. Very complicated procedure to get the silver on the inside of the plastic, like the aluminium on the inside of the plastic. Yeah, serious engineering to build that thing. 200 packets and 31 of them have holes, and we want to know, well, what percentage of packets of chips have holes in them? And you go, well, obviously 31 out of 200, great. But that's just for my sample, and I want to know, well, based on the variation, what could it be? Okay, and is it, well, it's obviously not 0, is it over 5%, which is our cutoff where we decide that it's really bad? Okay, and so that's the sort of question you could be asking. And so we have, let's just think about this. My chip packet has 2 categories. It's either got a hole or it doesn't. That's a chip packet, not a person. And we write down whether it has a hole or it doesn't. And our question is, what is this? How often does that happen? That's our question. Okay? We have a yes or no outcome, and we're interested in just one of those options, and we want to know more about it. Well, that situation, that's exactly what this row of the table is for. Because we are estimating a proportion. And we're interested in how it varies. That's how I think about this. Each packet we've written a yes or no outcome, we're interested in the proportion of one of those categories. And that's what this thing here is about. So the focus at the moment is on the thing that we are estimating at the moment. That helps us make the decision. But that proportion, ultimately came back from looking at individuals and having a yes or no outcome for each one. So thinking about what you would have to record about each individual object in order to get this is useful. So you'll notice that these two, in fact all of this, these all go with categorical outcomes. Okay. So it's a Z, right? I wish they had names. This is a Z, the normal distribution with 0, 1. So I name them by the variable involved. So these all go with a Z. But you can call them a P for proportion if you prefer. So this is a... This is the row of the table that you're going to be using. So some people call that the one proportion Z test, or a one proportion Z confidence interval, because Z is the letter we use for the standard normal distribution. Okay. Then we might ask ourselves, let's think of another question. This is really hard for me. I'm not doing very well. Have we got one? Oh, no. So, does the time of day make a difference to something? Got to pick an outcome. What objects are going to be different in the morning compared to the afternoon? Sorry? Okay, position of the sun, obviously. Yeah. Temperature, yep. Let's do a car. It should, right? It should be hotter in the afternoon if they've been sitting out all day. Maybe you're designing a car and you want to choose, you've got this fancy new paint and you want to see how it what happens to it. So does time of day make a difference to temperature of the car? And so we've got our cars. This is a very bad car. You see, it's got wheels, it's got a windscreen, it's good enough. And so we've got morning, afternoon. That's what we're going to do. And temperature. And temperature is a number. So we are interested in whether this category makes a difference to this number. Now, statistics is not actually very good. It never tells you whether something causes something. It just says whether it's numerically related. You have to decide whether it causes something based on your how you've collected the data. But we're interested in this. Well, here's a question. Are we going to do this? How are we going to do it? Are we going to have the same car at 2 different times of day? That sounds reasonable. Perfectly reasonable. Do the temperature measurement on each car twice. All right, cool. So each car is in both of these categories. Well, that means we're with paired data, because there's a pair of numerical measurements for each outcome. So this is the paired t-test. This one here, paired comparison. So when I say t, that's referring to this thing. Yep, that thing there. Paired comparisons, the thing I'm interested in is the difference between each temperature and that. So the way that we think about this is that each of them, we actually didn't measure this. That's not what it looks like at all. What it looks like is a morning temperature and an afternoon temperature. And everybody, we want to know how morning versus afternoon affects this outcome. That's the picture in our head. how does this affect that? But these are not real variables, they're just categories in which to measure it. And so the way that we're actually going to do this is we're going to find a difference. Morning minus afternoon or something like that. Probably afternoon minus morning makes more sense just because it should be hotter in the afternoon. But yeah. It's very hard to talk through in the way that I'm doing at the moment, I'm sorry. The reason I do this is that if I can draw a picture, then it's easier for me in my head to respond to a picture than it is to a wall of text. And that's why I do it this way. So each of these can go with the situation. It would be really cool if I had some questions, like an exam or assignment question, where we would have to make the decision properly, instead of me making up the story. Does anyone have any on hand? What's that? Oh, yeah. Oh, cool. Like this one, for example. In an experiment to compare two different methods of measuring the wall thickness of cylinder heads, 2 measurements were made on each of 18 cylinder heads, one using ultrasound and one by sectioning. The purpose of the experiment was to determine whether there is a systematic difference between the 2 methods of measurement. Okay. E.g. page 86 of notes. Okay. I don't know what a cylinder head looks like, so I'm just going to draw this. Okay. So my cylinder head. Let's just think about exactly what has been written down about each cylinder head. We have a measurement using ultrasound, and that would be a number, I guess. And we have a measurement using section. So every cylinder head has 2 measurements. Beautiful. Okay. And the question, just to say, that's the story, that's what's been recorded about each individual. And then let's just see, compare 2 different methods of measuring the thickness of cylinder heads. The purpose was to determine whether there was a systematic difference between the 2 methods of measurement. So basically, does the measurement method make a difference to the measurement? That's what we're asking. So we're asking measurement method, which is either ultrasound or sectioning, does it make a difference to the outcome? That's what we're asking ourselves. And every cylinder is in both of these categories. So it's a paired situation. So we're going to do a paired test, and it's going to be a T eventually. So that's why they've used this. And the only way, and the way to figure out what to do with the paired comparison is to, for every one of them, calculate a difference. And then change your question to, aha, now I want to just ask, is that difference 0 on average? How does this difference change across different cylinders? Yeah, so if you look what they're doing here, they go D is the first measurement minus the second measurement. And then they ask ourselves, then they do all the things, sure. So they've asked it to do a t-test. And it's given me a confidence interval to say that the differences are between here and here. Well, the average difference between here and here. Or a p-value even, to tell you actually, if that p-value is large, then I declare that this doesn't make a difference to this. P-values are about don't let a statistician hear me say this, but p-value is a measure of similarity. A measure of things being the same regardless of what the input is. And so if that p-value is high, that indicates that this outcome measurement is the same regardless of what this is. So it doesn't make a difference. So that's good. So my ultrasound and my sectioning are the same. Might as well do ultrasound because then I don't have to break my cylinder. Beautiful. And they do that in medicine as well. It's like, this invasive test that requires us to actually cut you open produces the same information as this ultrasound. We're going to do an ultrasound. Okay. All right. So you can now start thinking of all your engineering things to say, well, how does the cylinder feel about it? Okay, let's see if I can find another one. Where are all the stories in here? Stats is meaningless without a story. Oh, I've gone way too far back now. We're in distributions now. Oh. These notes are weird. Useful advice for you, don't use these notes. No, meaning make your own. Pull out the bits that you need and put them on a separate piece of paper. Because flicking through this thing, not productive. I can't find any more stories. Look, I do have another seminar on this. You can go and have a look at that. And feel free to come and chat in the Maths Learning Centre about it if you want to. Maybe next year, for next year's students, I will come prepared with a list of actual problems. Really, it comes down to these pictures. And every one of these has a picture to go with it. And I'm going to draw in Saxon's book here. He's now immortalised forever. Oh, look, I can. So look at this paired comparison. That's category to number, and every individual is in both categories. This binomial CI, no, I can't do it on here. It's stupid. I'm going to do the headings from your table, if that's okay. I don't like that one. Okay, so that's one of the headings from your table, and the picture that I have that goes with that is just a numerical outcome, and you just want to know where is the centre, right? That's all it is. There is nothing affecting the outcome. You just got some raw numbers. 2 independent samples. Well, we have some category affecting a numerical outcome, and every individual has only been measured once, like they only exist in one category. So the classic one of this is where you're testing what happens when you have 2 different machines producing objects. You can't have an object produced by 2 different machines. Each object can only be produced by machine A or produced by machine B, and they're separate objects. And then there's paired comparison. Which is the same story, the same question, but this time every individual is measured in both categories. And I should just draw something extra here. About each person here, I write down which category they're in and what the measurement was. Whereas in this one, about each person, I write down what the measurement was in category A and what the measurement was in category B. That's the difference between these two things. So these are the hardest to make a decision between because you have to focus very carefully on when and how the information was recorded about the objects that are involved. So the binomial confidence interval or binomial test is about asking, you've just got a category measured for each individual, and you're asking, you know, what is this percentage, basically? What is the proportion? Statisticians are allergic to percentages. They always write decimals. Unless they say a 5% significance. I don't know why. It can actually be multiple categories. As long as you're only focusing on one of them at a time, it'll be okay. The next one on the list is 2 proportions CI. And that's saying that there is some situation category and you're asking an outcome which is also a category. And you're always focusing on just one of the outcomes, the yes or the no. But the easiest thing for me to do is sit down and go, okay, for each object I've written down what treatment I gave them, A or B, and whether the thing happened or not, yes or no. And I'm going to just focus on whether it happened, yes. The classic one they give you is like election results, which is so not engineering, but still makes the point. The one I give to my students about the chili is instead of actually measuring my friends' temperatures, I just ask them if they feel hot. So, do they have chili, yes or no? Do they feel hot, yes or no? And I can see whether the percentage that said yes is higher in one group than the other. It's not science, but it does stop me from having to stick things in my friends' mouths. Or other places, depending on how precise I want to be. Have any of you seen the Recess movie? It's a really good movie. So, no, I'm just imagining a scene in it. So, your mum's going to want to take your temperature. Oh, I'll get the petroleum jelly. You can tell that I'm already almost 2 hours into this seminar. I've gone a bit loopy. And then regression at the very end here. Regression is designed for this situation. When everybody has a number and another number measured. So for example, that I have 2 numbers measured and I want to know how they affect each other. So for example, I could try and investigate how thick I lay on the paint and what the temperature is, for example. That's an example. I could have cars and I could do the paint thickness and the temperature and measure them all with different thicknesses of paint and see what the temperature is after an hour. And see if the thickness of my paint made a difference to the temperature. Hopefully, I don't know what the point is. Maybe you want it to be hotter, who knows. That's what regression is for. And regression, there are 3 different questions that you could ask. So you could ask yourself, is there a relationship between these things at all? Okay, in which case you would ask yourself, well, if there was a relationship, then as this thing increased, that one would either increase or decrease. And so there would be a slope in my diagram. And so you would be asking yourself, is the slope equal to 0? But instead of saying, is there a relationship, you wanted to know, well, how strong is this relationship? Maybe not how strong. Strong is the wrong word that has a specific meaning in statistics. You know, how much does A affect B? Then you're actually still looking at the slope, but this time you wanted to know what are the options for what this slope could be, so you'll need a confidence interval. Okay, a confidence interval is designed to answer the question of what could this number be, whereas a p-value test is designed to answer a yes or no question. So us asking, is there a relationship at all? Well, if there wasn't, the slope would be 0. Let's ask the question, is it equal to 0? P-value will tell me yes or no. High will tell me it's similar to the thing I was thinking of, and low will tell me it's different to the thing I was thinking of. So a high p-value would tell you that the slope is 0 after all. Well, or it could be, or at least I don't think it's not. It's all double negatives in statistics. Whereas how much does A affect B? I'll be looking, well, you know, it's between, for every increase of 1 micrometer of paint thickness, the temperature goes down by between 6 and 7 degrees. Right, that sort of thing. And the only other thing you could be asking is, well, just a second, how much does A affect B for an individual? So given that I know what A is, what could B be? And this is the prediction interval. A prediction interval is answering that question. So those are the 3 rows in the table for regression here. Regression is always this situation, but these 3 different questions have different ways of answering them. So this one is saying, well, what could the slope be? How much does increasing 1 of A affect B? But this is saying, given I know A, what could B be for this specific object? And that's a prediction interval. And so that is the interesting thing, is that the actual question you're answering also changes what you do. So that's those 3 things on the first page are what makes the difference. What variables are involved? What question are you answering? And how is your data arranged? And they make a difference to the results. And if you did even more statistics, there would be even more options for how these things went together. So at the moment, you only have this data arrangement question for the category to number situation. But you could conceivably do it. You've got, see this one here, where you've got people are measured in different situations and you've got an outcome, yes or no. You could you could give everyone a meal with chili and separately a meal without chili and do the yes or no with both. And then that would be a paired 2 proportion test, whatever that is. But you didn't do that in your course, but all of the options are possible. And in a full statistics course that takes a whole semester instead of 4 weeks, you would have covered it. Actually, you wouldn't. They don't do it at all, which is really sad. They do it over in psychology, but they don't do it in the maths degree course. Okay. I hope that helped. I mean, it's how I think about it. Yeah. Okay. I should put that title back here. Okay. Well, I did let the recording go for 2.5 hours, so I could do something else if you really wanted me to. I won't be offended if you leave. So if anyone has burning desire for one of these other things, most of them look like they're like, I can do one of them pretty quick, I reckon. Are you able to stay around for a bit?
I feel like it's better to go through the house and more.
Okay, cool. You can ask that one at the Maths Learning Centre then.
The one I want to ask is the exact day.
I know. Yep, cool. Well, let's talk about these power series then. Okay. Oh, I did want to just... I think I can answer the complex Fourier series one, that specific question. I'll do that first. I'm not going to show you how to find a complex Fourier, but what I wanted to talk about was how to get from the complex one to the ordinary one. Because that was the specific question that somebody asked me. I don't know who it was. I can do that one. So, the idea of a Fourier series is to rewrite your function in terms of sine and cos, usually. Something like that. Something like that. That's the whole idea of a Fourier series. And the reason you can expect to do that is that the causes with various different frequencies and the sines with various different frequencies together, I'm going to use a fancy maths word here, are an orthonormal basis for the vector space of functions. Yes! So in the same way as in algebra in Maths 1, you could write vectors as a combination of a basis. We can do it with functions too. And cos and sine are sort of linearly independent from each other. You can't write one in terms of the other without fiddling with what's inside them. So that's cool. So that's the idea of a Fourier series. A complex Fourier series, I mean, this is what we do to real functions. And the thing is that when you have cos of an imaginary number, then it turns out, because of Euler, I think, that turns out to be e to the power of something. And so if you want to do it in complex numbers, you get I'm going to have to look that up. I think it's just NIX. Pi on, oh, damn it, I'll just look it up. Can never remember this one because I never did a course with it in it, and I'm only doing it from helping people, and I only get to do this once a semester, once a year. So it was before the separation of variables. No, I was right. Good. So it's traditionally INX, but whatever. Nix is kind of cool. Okay. The reason why this works is that these functions are also a basis, and within them they contain causes and sines. Okay. So useful information. E to the I nx is the same as cos nx plus I sine nx. E to the I anything is cos of thing, I sine of thing. That is what Demois, no, that's not. Euler probably. That's what the people who studied complex numbers when it was early days, like in the 1750s to 1850s, that's what they discovered, that we could write complex powers using sine and cos, and it was, yay, we all celebrated, and now we have this. So that's the most useful piece of information that we have here, and this is allowing us to link these things together. So I believe it's traditional to call these ones little a and little b. You'll notice that when I solve differential equations, I always put the a with the cos and the b with the sine, and that's because of Fourier series. Also, I just think everything should be in alphabetical order. So, cos is before sine, so a is before, and a is before b. Yay. Which is why when I do like a linear function, I'll go a plus bx, because they're in order of powers of x, and then we're in alphabetical order for the numbers too. So it's not just bad. It's not just a bad idea to do that, because a constant is cos of 0x is a constant, and so the a as a constant is technically a cosine function already. It's a times cos of 0 times x. And y equals x is an odd function, and so is sine. And so it all works out neatly. Okay, cool. So these are going to relate to that somehow, and it's going to be, but let's just look at something else. E to the minus I in x will be cos of minus nx. But cos of minus something is the same as cos of plus the thing. And so we end up with this. And I'm going to get sine of minus nx. But sine of minus a thing is minus sine of the thing. So we're going to get this. So if you put a positive n into here, you'll get a plus here. If you put a negative n into here, you'll get a negative here. And so it will turn out that if I add these two together, I'm going to get 2 lots of cos nx. So if I have Cn and C minus n, and I add them together, it's going to give me the coefficient of cos nx. And so the an is Cn plus C minus n. That's what's going to happen. So if I have this, damn it, there'll be a Cn here, C of minus n, C of minus n, minus C of minus n. And so if I get Cn e to the I n x plus Cn minus n e to the minus I n x, I get Cn plus C minus n lots of cos nx. And if I subtract them, so if I go this minus this, they'll cancel out. I'll get ICN minus minus IC minus n, so I'll get this. And so what this is telling me is that I need to get the coefficient of cos nx, I need to go C of n plus C of minus n. Fabulous. As long as this is basically figured out from not knowing anything other than this. So the question is, assuming that I know what the CNs are, I should be able to just do this, and that will tell me what they are. I'm going to do this and then divide by I. And that will tell me what the one is that goes with sine, and I'll just add them together. I'm just making it up at the moment, and we're nearly there. Okay. So just a second. Oh, cool. They've just said in the notes here that C of n is actually the complex conjugate of C of minus n in the notes here. Okay, and so therefore so if I add a number to its complex conjugate, the imaginary part will go away, and I'll end up with 2 of the real part. Like that. All right, there we go. We've got it, and in a similar way, Bn will be 2 of the imaginary part of Cn. I think it's minus 2. No, that doesn't make the slightest bit of sense. I've done something wrong. Oh no, that'll be a... No. Give me a second. So... I think it comes out to be a minus. See, nobody understands this, really. So, well, to be fair, I have had no lectures on this ever in my life. Now, that's not a good excuse because I managed to figure out all the other stuff, never having lectures on it either. But the earlier stuff in the course is easier for me to deal with. It looks to me, according to your notes, scrap that. According to your notes, it says that Cn is a half of An minus Ibn. And that would tell me that if I did the real bit of Cn, I should get a half of An. And if I did the imaginary bit of Cn, I should get minus a half of Bn. And so that should tell me that An is 2 lots of the real part of Cn, and Bn is minus 2 lots of the imaginary part of Cn. Because these bits are real, these bits. That's what it says. This is from page 62. Okay. So when we did the assignment this semester, when we did this complex Fourier thing, most of them were 0 for one of them, because they were mostly purely real, and so the imaginary bits were all 0, and so we didn't get coefficients there. But there was one coefficient that was purely imaginary, and so we ended up with not the real bit, nothing for the cos, but a bit for the sine. Yeah. I still don't believe it yet, but I'm going to move on. This is what the notes say, so I'm going to believe what the notes say. Okay. So, power series, doing well. Okay, so you know how I said that we had stuff like this? And we would normally solve the homogeneous bit first. Not a G. And then I was also saying how that only happened while we were had constant coefficients. This part for the homogeneous bit, we only knew how to solve if the coefficients were constant. Well, power series is one of the ways of dealing with it when they're not constant. So, here we go. So power series help when those two things aren't constant. And that's why we might want to do it. And so we'll still, even if we use power series for this homogeneous bit, we would still have to use still have to use the undetermined coefficients or the variation of parameters to figure out the particular bit. Whoa. Okay. So, the goal, so this will be different depending on the kinds of functions that you have. So if your functions are polynomials, it'd be great, you can use an ordinary power series. So x equals 0, for example, so they're polynomials. Doesn't have to be polynomials, it could be sine and cos, but it doesn't really matter. Then an ordinary power series will work. Actually, do you know what? They're not even supposed to be this. They actually literally have to be polynomials. I.e., they have to be polynomials. Then you can use an ordinary power series. Like that. However, if they're not defined when x is 0, actually you really need them to, if they're not defined when x is 0, that's when we use Frobenius's method. There are some technical details there. It's not good enough. Frobenius's method still won't work if they're horribly not defined when x is 0. So if they need to be, so just an aside, undefined when x equals 0 is what they call a singular point. X equals 0 is a singular point. Okay, so if it was undefined when x equals 2, that would be a singular point as well. X equals 2 is a singular point, but we normally only focus on when x is 0 because we have power series here that just have x. If we wanted to write one that said x minus 2 to the power of n, then we'd need to worry about what happens when x is 2. But we normally don't care because just having x is easier. So that would be a singular point. That's what it means to be a singular point. I believe the official term is not analytic at that point, meaning it doesn't have all of its derivatives. Like, well, it's not equal to its Taylor series, which is fine because that's what we're trying to do here. We're writing a Taylor series by doing this thing. You need it to be what they call a regular singular point. Yes, you need it to be what they call a regular singular point in order for Frobenius's method to work. And for x equals 0 to be a regular singular point, you need basically, if you multiply everything by x squared, then they will have to become defined, basically. But I'm just going to check that. I'm almost there. Yeah, anyway. Okay, so as long as that works, basically as long as when you multiply the bottom the denominators by x squared and it all becomes polynomials, it should be fine. But I'm trying to find where it says that in your notes. Yeah. Well, there's the meaning of regular singular point. There's the word, but it must be defined before that. Singular points may be regular or irregular, more on this later. Power series. Power series. It's a regular singular point if it's a singular point and both of those are analytic functions. Okay. So you need a special kind to work. So you need, so in the purposes of x, you need x times px and x squared times qx. Basically to be polynomials. But you need them to be analytic, meaning that they're defined there. They're not allowed to be undefined at that point. But really, Frobenius's method will only work if they're polynomials. Okay. Cool. So the power series thing will, an ordinary plain power series will work as long as it's defined when x is 0. Frobenius's method is going to be required if one of those functions is undefined when x isn't 0. So when x is 0. But they both use similar methods of assuming that's a certain format and then differentiating and subbing in and seeing what you get. Which of them would you like me to give an example of? I guess the Frobenius uses more stuff and it's the same idea generally, so let's do that. Let's do that one. I'm just making one up. Okay, so in order to tell if I'm able to do this, I'm going to have to put it in standard form. Like that. And that tells me that x equals 0 is a singular point. Because these functions aren't defined when x is 0. It's a regular singular point because when I multiplied them both by x, they became defined again. Regular since x times 1 over x. It's 1. And x squared times 2 over x is 2x, and they're both, what was the word? Analytic. So analytic means it has all of its derivatives at every point, at the point you're interested in. And so in our case, it's only going to work if they're polynomials anyway. And so then what we're going to do is we're going to go technically, I think you put the x equals r out here. But you normally do this. So importantly, the r might be seriously hoping this works. I may have to go back and change the question. Importantly, the r could be a negative number, so it may be that you've got like, you had 1 plus x squared plus whatever, but then you had r equals minus 2, and so you had to divide everything by x squared, and so you got 1 over x plus 1 plus x, that sort of thing. You can probably have this back if you wanted. Okay, so what we're going to do is we're going to differentiate it and we're going to sub it in. And we're going to sub it into the one that didn't have any x's on the bottom. I'm going to go back to the original one. So if they gave you one that had x's on the bottom to begin with, you'd want to multiply it out to get to something where there weren't x's on the bottom, and that's the one you want to sub it into.
Does it make a difference, or is it just easier?
It probably doesn't make a difference. I've never tried it another way, so one day maybe I'll try them both and see which seems easier and whether they come to the same answer. It shouldn't make a difference. Yeah, this one would just mean that your powers would go down, and this one means the powers go up. And in general, it's easier to add things than subtract them because minusing means you lose minus signs. It's just dangerous. So I reckon it should work, but it'll be easier if you do the other one. But usually they'll give it to you in this format to begin with anyway. So it'll all be good. There were some good what-if questions. Thank you. So y dashed. So when I differentiate x to the n plus r, the current power will multiply and the power will go down by 1. If the r wasn't there, then when n is 0, you get an x to the power of -1. And that's not really true. So normally if you're doing not Frobenius's method but the ordinary power series method, you make this start at 1. But it doesn't really matter. So when the r is there, we don't know if the r is like a half or something, and so we're going to need to keep all of those. So we're going to have to multiply by the next power, and we get that. Okay. Cool. Now I'm going to do something that's probably not the way the lecturer does it, but it makes sense to me. I'm going to need to sub this into there. So what I'm going to do is I'm going to write down what each piece of those is. So x times y double dashed. So if I multiply this one by x, the power of x will go up by 1. And then I just have a straight up y dash, which I already have, but I'm just going to copy it just for my own purposes. And then I have a minus 2y. Now I'm sure there are ways of doing this that avoid you having to write them all down over and over, but this is just to show you what I'm doing here. So the idea is that if I add all these three things together, it's supposed to come out to 0. So that means that the coefficient of every power of x should be 0. Which would be great, except this one doesn't match up with those ones. So I'm going to have to shift this one over so that it has the same powers of x that these ones do. Okay. So I want it to be r minus 1. So I'm going to have to take 1 off of all of the n's here. And then I'm going to have to add 1 over here to take into account that change I made. So here's the idea. I make this go down 1, which means I need to make that go up 1. So all the n's here go down 1, and the n's here go up 1. If I wanted to shift it forward to r plus 1, then I would add 1's here and subtract 1's here. But of course, infinity minus 1 is still infinity. And infinity plus 1 is still infinity. Because infinity isn't really there, actually. There is no infinity there. It doesn't actually end at all. And so we're not really adding, we're adding 1 to all of the n's simultaneously. Okay, that's how you do it. To shift it over, you add 1 or subtract 1 here and do the opposite in the sum there. Okay, so now they all match up. Okay, and when we add them all together, it's supposed to come out to 0. So therefore, every coefficient is 0. So coefficient of x to the whatever is 0 for all n. That's what I'm going to need to do. All the coefficients have to be 0 because the whole function is 0. So I'm going to run through all the coefficients, all the values of n, and look at the coefficient of each one separately. So I'm going to look at the values of n that I have, and I'm going to use each one until I can get to the point where they all have n. So let me say what I mean by that. This sum starts at 0, this sum starts at 0, this sum starts at 1. So it's not until I get to n equals 1 that that number n is involved in all 3 of them. So this one involves only n's that are greater than or equal to 1, this one involves n's that are greater than or equal to 0, this one involves n's that are greater than or equal to 0. So when I have n equals 0, it only is part of these 2. When I have n equals 1, it's part of all 3, and every n after that will be in all 3 of them. So that's what I'm going to do. Anything that's only involved in a couple, I'll do that separately, and anything that's involved in everything, I'll just call it n. That's what I'm going to do. So when n equals 0, because it's only in the first 2 sums, I'll do it separately. So when n equals 0, the coefficient of x to the 0 plus r minus 1, that's what it is when n equals 0. So let's see. A 0, 0 plus r minus 1, x to the, well, we don't need the x because we're doing the coefficient. And this one is a0 like that. That is the coefficient of x to the 0 plus r minus 1 when n equals 0. And this one doesn't start until n equals 1, so it's not involved. Okay, and this is supposed to be 0. Oh my. That's got to be special. That's I don't know what that means when I get a double root, but anyway, we'll see what happens. I really didn't want it to be 0. Oh well, because now it's just an ordinary power series. But anyway. Ah well. That's my fault for choosing a bad combination of numbers. This is the indicial equation. Well, at least if I remove the a0, it's the indicial equation. So the idea is that if you take the earliest n that appears anywhere and you take the coefficient of x that goes with that, it will produce an equation that has a0 and r in it. And so we're going to get that's the indicial equation. The reason you do that is you go, well, if a0 was 0, then we're going to make a recurrence relation eventually, and that will make everything else 0 as well. And so we assume that the a0 isn't 0. So that will happen. If you pick the very first n that appears anywhere, it might be -1, it might be -2, it might be 4, and you find the coefficient that goes with that, it will produce the indicial equation every time. Okay, so let me have a look. The next n is 1, and 1 appears in all three of them, and so, yep, that's okay. So therefore, if n is greater than or equal to 1, I can just do it in terms of n. Some of these problems, you do n equals 0 and then n equals 1, and it doesn't start until 2 that it's in all three of them. So you have to do two n's separately, but only the first one is the indicial equation. Okay, so we get, so the coefficient of x to the n plus r minus 1. We're just doing it in terms of n, since it doesn't matter which n I pick, it's in all three of them. And so I've got an n plus r minus 1 plus n plus r plus minus 2an minus 1. And that's supposed to be 0. So my goal is to find a formula that will tell me what the later an's is from the earlier ones. So what you need to do is rearrange this so you have biggest n, a of the biggest n equals whatever. So here is my biggest n here, because that's an n minus 1. There's all my a's. And so there's my biggest n there. So I'm going to rearrange it to get an equals. If my biggest n had been an plus 1 or an plus 3, I would have rearranged it to get an plus 1 or an plus 3 equals. Whichever has the highest value of n is the one that you make it equal to. So it just makes it easier in the end. So what have we got? We've got, oh, we can factorise that. That's kind of nice. So I did two things at once there. I pulled this over that side, because I'm going to have to pull everything that doesn't involve an over there eventually. And I noticed that both of these had an n plus r in them, so I factorised that out. And that is n plus r again. And so my an is now 2 of an minus 1 over n plus r squared. That's my recurrence relation. And the place where your recurrence relation begins is the place where this thing that we did begins. If this thing began when n was 2, then this recurrence relation only applies for n being greater than or equal to 2. And so what this allows me to do is to now say that whatever A0 is, I don't know what A0 is, but I can figure out all the other ones in terms of it. So A0 is just A0. A1 is 2A0 over... the R is 0, isn't it? We actually did that. We already said the R was 0. So we can actually put that in here. I should have done that. Damn it! I'm going to redo it just a second. It probably makes more sense to choose the R to be 0 and do it all in terms of that number at this stage. So can I just redo that? You could do that if you wanted. But instead, we're going to do... Okay, so I am going to copy what I had before. So I'm going to go, well, we know that R is 0. And so I've got n minus 1 plus n minus 2 an minus 1 equals 0. Beautiful. Okay, the R's aren't in the way now. If you've got two different values of R, the lecturer normally tells you which value of R that they want you to use. But in practice, if you really wanted to do this, you would normally say, do it for both. Okay. So, cool. So A0 is whatever A0 is. A1 is 2 times A0 over 1 squared, which is whatever 2A0. A2 is 2 times A1 over 2 squared, which is a half of A1, which is a half of 2 times A0, which is A0. And you could just keep going and figure out what everything is in terms of A0. Yep. Oh, crap. Yeah, that's fine. And A3 is 2 times A2 over 3 squared, which is 2/9, and A2 was A0. And so we can write everything in terms of A0. Yay! So that means that we're going to get that actually y is A0 plus A1. Well, just a second. Y was this, wasn't it? Was that, but the R was 0. And so that's... Sorry? This here, that's a 2 over 9. This is an A2 over 3 squared. And that is a 2 over 9 times A0. Okay, and so this is A0 plus 2A0x plus A0x squared plus 2/9 of A0x cubed, and so on. So we could pull the A0 out the front and we just get A0 times this thing, whatever it is. Okay, so we need to do some what ifs. Of course, if this R had turned out to be 1 or a half, then all of these would be out by that. You know, what if R had been a half, and then we would have gotten n plus a half, and so we would have gotten A0 x to the half plus A1 x to the 1.5 plus A2 x to the 2.5, and so on. It's just important to know that that's what would have happened if the R had been a half. We would have had plus a half on all of the coefficients, like that. Yeah. And then you could have subbed in the A0s and whatever. All right, there's 1 minute and 40 seconds, so I'm going on the timer for the recording, so I'm going to stop there. But you have enough time for one question, if you want it on the recording.
What's the indicial equation?
What is it? It is, as far as I know, it is literally just the thing that you get to tell you what R is. So it's the equation that tells you what R is. So I only know it in this context. The indicial equation is the equation that tells you what the value of R should be, and it's the equation that comes from the coefficient of the earliest n. I think indicial just means it indicates something. I wish I knew. I hope that was satisfying.
Also, David, you said there was a chart.
Yep.
On the Maths Learning Centre?
So on the Maths Learning Centre website, just let me show you. No. So, this is the Maths Learning Centre website, and these are the resources, and it's in alphabetical order. That's Eng Maths IIA. This was in the email I sent, a link direct to this page. So if you come down here and look at differential equations summary,